Hello, this is Mr. Linares again. We're going to be talking about some basic circuit construction and the things you need for a circuit, the general names of the parts of a circuit, a few specifics, and then how to test these circuits. The circuit you have here in the video right now is called a series circuit. That means it goes from the beginning of the power source back to ground, or the negative part of the power source, in one pathway. No breaks, just one pathway. What we have here, see my handy little hand like that? We've got a power supply back here that is plugged into the wall. This is taking the 110 volts that comes out of the wall, changing it to 12 volts. We use 12 volts in our class as just a basic standard because it's an easy number to work with. In reality, when working with vehicles, you will be dealing with between 12.66 volts and about 14.5 volts, depending if the car is static or is running, and also depending on if you're dealing with a computer system with regulated voltages in it or not. When you start dealing with power systems involving computers, you may deal with 5, 8, or 12 volts, depending on the manufacturer you're dealing with. However, these day and age, with all the cars out there that have various computer systems and various accessories, these things may change. Bottom line, when you're dealing with circuits, no matter what you have, no matter what you're dealing with, you do have a power supply of some kind. That could be a car battery, or when the car is running, the alternator, or if you're in a lab like ours, a power supply that takes the house power and transforms it to 12 volts, a step-down transformation, step-down transformer, power box, okay? Now, our power supply here does have a fuse in it. So this brings us to the first two components you need of a circuit. You need a power supply. You need a circuit protection, which has a fuse in it, and it's built in here. Normally, we would have a fuse right out here, but since we have it fused in our box, we're going to use that. You need a wire, a conductor of some kind, which you see all over the circuit here. Okay? A conducting path for that circuit. So I'm going to move this out of the way, it's a little busy here. You need a control for your circuit. This is a switch. It turns the circuit on and off, or in our terms, open and closed. An open circuit is a broken open circuit. It does not flow current. An open circuit does not flow current through it. Okay? This is either if it is due to a control like a switch, or because of a fault, like a circuit failure, like something broke or got cut. Okay, so you have your power supply. You have a circuit protection, or like a fuse. You have a pathway for your current flow. Okay, that is the wire that goes from the beginning of the circuit through all the components back to the end of the circuit. The positive part of the power supply all the way through to the negative end of the power supply. Okay, or B plus to B minus, or positive to ground, or hot to ground, all right? Positive to negative. So far, so good. Power supply, circuit protection, our conducting path, our control, which is our switch. Then we add in a load, okay? A load or a consumer. This could be something as simple as a light, okay, that'll turn on. Okay, that is crazy bright right there. You see that? Wow. Okay, in our video here. So I'll be working around this brightness of this light here. There's not a lot I could do about that unless I change the light bulb type in there. And this is a function of resistance, which we'll talk about in a little bit. Okay, so let's see here. I wonder if Mickey Mouse's hand can turn this thing off. I don't think so. I'm not going to fool around with that. So I'll just reach in my big old paw and do that. Okay, so let's review. Series circuit. Okay. A series circuit is the most basic construction you could have for a circuit. This is the simplest setup I can conceive of. We have power supply, circuit protection, circuit path, a conductor. Okay, that means your wire. A control, like a switch or a button to open and close the circuit. A load, this is the thing that is using up the voltage, the thing that's consuming the voltage. Okay? If you didn't have the voltage consumed, you would not have a circuit functional, okay? Because we have electrical pressure built up in the power supply. That power supply exerts that pressure throughout the circuit up until up to our load here. The load provides the resistance okay, that pressure is pushing against, the current's going to flow through it. It's going to give us our light because of the resistive nature of the little filament that's inside, and then the residual goes back to ground. It gets used up. The electrons flow there after they trickle in after they've been used up here. Okay, the pressure has been used up to light this up. So what we have here is our circuit, and let's start showing some of the values using a meter. Okay, so we bring this meter on in here. This is our digital multimeter. This is a Fluke meter, which is generally speaking the industry standard. Notice it's beat up a little bit. That's because it's been around for a long time in good service, and it is still functional because I've taken care of it. Even though it's a little grungy looking, the basic parts of it are still perfect condition because I've taken care of it. Okay, only the outside's a little grungy. All right. Now I'm going to go ahead and zoom in here, so please forgive my iffy camera work here. Let me move this up here a little bit and flex this. Again, I do apologize. I'm not the best camera person in the world. Okay, let's zoom in a little bit more. You see that V that it is pointing to right there. That V with the solid line and the dotted line right there indicates direct current voltage. The V with the wavy over it is alternating current. When we're dealing with automotive systems, we will be dealing exclusively in our class, okay, until we get over the major hurdles at any rate, with direct current. So when you have voltage set up, that is where your meter is going to be. Okay, up there you see a range button. Most of the meters you're going to be dealing with auto range. If you look in the upper left corner there, it says auto, meaning once it starts to read, it's going to automatically go to the most readable value it has. I like to leave mine there just to make things simple. However, if I do push the range button, I can move my decimal point and keep it static where I want. There's going to be more of this when you start learning the meter certification for Snap-on in our class. But you're not going to be using a Fluke. You'll be using, you're going to be using a Snap-on meter. Okay? Now, back down to here. Again, we're on volts. Our leads. If you look at our two leads, you have the black in common, or COM. That lead will stay there regardless of the reading that you're taking. You're going to notice that the red lead is here in V for volts. It's also got the symbol for ohms, the horseshoe there, the omega symbol for ohms. So volts and ohms is going to be in this port right here. And then over here in the A port, okay, whoops, right there, you have amperage. We're not measuring amperage yet. When we get to that, I will show you. So for volts and ohms, it's going to be here. Common is going to be here no matter what, the black lead, the negative lead. And then over here for amps when we get to it. Okay? So for right now, we're going to test this series circuit. I'm going to show you some of the concepts of voltage that operate inside of a circuit. Okay? So please bear with it. Hopefully you can see here. If my hands get in the way, I do apologize. But what I will do is I will set things up, turn things on or off as I need to, and then step back to make my point so you can see things clearly, okay? And we could still see that meter, it still reads 0. So here we go. Okay. Now, what we've got going on here is our series circuit in action. We have 12 volts of power coming out of this power supply. How do we prove this? We go to our power supply and we put it in the positive and negative, and we show our 12 volts here. That shows that our power supply is in fact good. Okay? Now, what we do is these leads are on the positive and negative, or the hot and the ground, or the B plus and B minus for battery positive and battery negative. For our initial testing, we're going to leave our negative lead on ground. In this particular box right here, ground exists at the black terminal over there, also in these terminals down here. So what I'm going to do just to make sure that this stays in one spot is I'm going to go ahead and put the black lead down here for ground. Now check this out. You're going to notice it still gives the same reading. As long as you have good contact between the end of your terminal, your end of your probe here, and whatever you're testing, you're going to be just fine, okay? So, first off, we're going to talk about voltage and how much voltage you have available at any point in the circuit. Available voltage means just that, how much voltage you have available at whatever given point. So at our power supply, we have an available 12 volts, okay? Right now, we're not worrying about the hundredths of a volt right there. When we come on over here to our switch, we also have 12 volts. After our switch, on the negative side of our switch, we have a little tiny bit less than 12 volts, okay? About 0.06 of a volt less. That's because the switch here consumed a little bit of voltage because the switch has a tiny, tiny bit of resistance. We come on over here to our light, okay? And we find that we've got nearly 12 volts, okay? A little tiny, tiny bit of loss happens in each path. But for the most part, 12 volts, okay? 11.9. Now, right here, you should, after the light bulb here, see most of the voltage go away, or for our purposes, all of it go away. That bulb, being the only consumer, the only load in the circuit, is supposed to eat up all that voltage, okay? Because that's its purpose. So we come over here and get into our terminal, and we see that it's virtually all gone. There's only 0.06 of a volt left over. That is good, okay? And then we go ahead, and then we, well, since this is the end of the circuit, if you really want to, you could come back over here and see that there's virtually nothing left right there, okay? Now, as that stands, that shows you that you have 12 volts applied, and when you get to your bulb here, or your load, your consumer, that's where you want it to eat the voltage, to consume the voltage, to use it up. And since the light is on, you know that it is functioning. Now, if you had a situation where your light was dim, okay, maybe there is something else consuming voltage as well in the circuit, okay? And that's going to bring us to our next little point here in the series circuit, which is the more resistance you add, the less current flow you have, but the voltage throughout the circuit is still going to all add up, okay? It's all going to get consumed, right? So right now, this bulb we have eating 12 volts. Now I'm going to leave that on. Listen to me, okay? I'm going to come over and I'm going to pick up another bulb that is identical to it. So we have another bulb that looks just the same, right? I'm going to go ahead and put that on in here. I'm going to go ahead and turn off my circuit. When you're working with circuits, for the time being, it's always good to turn them off before you start opening them up and moving wires. Eventually you learn when you can and can't get away with doing that. Let's get another lead, another wire here. Now keep in mind, these wire colors, they don't matter for positive and negative because they're all just conductors. They're color coded here just for your own purposes. You could have the green, the black, blue, whatever color you wanted, as long as they conduct, they will work. Now, once I turn this on, you're going to notice that these bulbs are going to be considerably dimmer, okay? Turn it on, and wow, that's awfully dim, okay? So what's happening, I'll show you. Let's go ahead and make sure that our negative terminal is grounded. We've got, playing the spaghetti games here. Sometimes this happens when you deal with wires. You got to make sure you're all squared away and everything's clear, because it can get kind of messy, especially with these educational test boards here, okay? So make sure you have 12 volts there. Okay, do you have 12 volts right here at the beginning of the circuit, the loads? Yeah, I have 12 volts. So wow, I still have that same 12 volts from before, more or less. But my lights are dimmer, so we got to figure out what's going on here, right? So what we're going to do is realize that since we have these two bulbs in series, one after the other, they only have 12 volts to share in terms of their consumption, okay? In order for that one of these bulbs to function at its best, it needs to have 12 volts. But since we don't, and they're in series one after the other, they have to share the voltage, okay? That means that this first bulb here, see, we have 12 volts, and watch. We come over here, oops, Make good contact. There's 6 volts left, meaning that this bulb only ate 6 volts. Now we come down over here to this bulb. That 6 volts is still available. And then we find out that, hey, this one over here finished the job eating it up. So we have 2 of the same bulb, okay, in the circuit. They're both going to split that voltage. They're going to eat it up at the same rate, okay? One after the other. If you want to hazard a guess as to why that is, give it some thought. Okay, I'm going to stop with the dramatic pause right there and just let you know. The reason these bulbs consume voltage at the same rate is because they have the same resistance, okay? Which is going to lead me into showing you how to measure resistance real quick here, all right? Just to make the point, then we'll get back into voltage here. So we're going to turn off our circuit, okay? Now once you turn off the circuit, there's no power available here to the bulbs, right? Nothing. So we know that we're good to go. Let's go and put this here. I'll leave that right there. These bulbs are identical. Okay, let it cool down a little bit. So you're going to go ahead and go to resistance up here. Keep this in the same hole because it's got the ohms right there. Poof. Okay. Touch your leads together. Okay, these leads have 1/10 of an ohm, 2/10 of an ohm for resistance, so we're good. A good conductor is only going to drop about 1/10 of a volt max or have 1/10 of an ohm resistance. Very low resistance, very low voltage consumption, okay? And any good conducting path. That is the wire, that is a switch, that is connections and things like that. The only place you want consuming voltage is your loads. So I'm going to measure this resistance. You have ohms right here. I'm going to go here, I'm going to go here. Notice that the part is disconnected from the circuit, okay? The reason is that an ohm meter creates its own private series circuit when it's measuring its values, okay? The meter becomes the power, the protection, and the conducting path, and that lamp is still the load, you know, or whatever it is else you're testing. It doesn't always have to be a lamp. It could be a motor or a solenoid or relay or something like that, okay? And this bulb has got 1 ohm, okay? Groovy. Let's disconnect this one up here. Let's see what we have here. This bulb also has about an ohm, 1.1 ohms. So they're going to consume voltage at the same rate. Now, check this out. If I go ahead and I bring in a different bulb, okay, I'm going to get a different value. 4.7 ohms. I'm going to go ahead and connect the circuit back up. And you're going to see something a little weird happen, and you might not like it. It might be surprising to you, okay? This bulb here has got a lot of resistance. This one, not a lot of resistance. 4.7 ohms and about 1 ohm, okay? Now, what I want you to consider before we turn this lights on is that Ohm's law. It takes 1 volt of pressure to push 1 amp of current through 1 ohm of resistance, okay? So if I need to move a certain amount of current to get a light to light up or a motor to go or whatever it is, I need to flow a certain amount of current through it. If I have too much resistance, I'm going to not flow through it, okay? If I put multiple resistances in a series circuit, I'm going to be consuming voltage at different rates. The more resistance a component has, the more voltage it will consume, which brings to this point right here. That light lights up. We know that this light is after that light though, right? Okay, so current has to be flowing through there at least. Check this out. Let's go ahead and ground our lead. Go ahead, volts. Okay. Come in here. We have our 12 volts still. Oops. Still have our 12 volts. Damn it. There we go. 12 volts. and we show over here, man, it hardly consumed anything. The reason this hardly consumed anything this time is because this one here, okay, consumed most of the voltage, because this one's got more resistance. The more resistance a part has, the more voltage it will consume, okay? Unless, of course, it is the only thing in the circuit, in which case it will consume everything in the circuit. The amount of resistance it has, a component has, when it is in series with another component, will determine how much voltage it consumes, all right? You need more pressure to get past more resistance. So here we go. Now, I'm going to go ahead and turn this off. Let's go ahead and review a few little things. In our basic circuit, we have the power supply and circuit protection. We have our wire, our conducting path, that's in all these sections right here. We have our control, our switch on off to open and close the circuit. We have got our loads that consume voltage. Sometimes it's 1, sometimes it's 2, sometimes it's 5 or 6. Who knows? Depends on what the purpose of the circuit is, okay? And then, when we're operating the circuit, we're applying voltage to the circuit. The loads of the circuit are going to provide resistance, and then current is going to flow based off of those values, okay? I go ahead and I take this circuit out of the loop. I'll get my normal flow back. You can see how bright this is right here, okay, how bright this lamp is, okay? It's going to be consuming 12 volts again, all right, because it's all by itself now. Likewise, if I go ahead, uh-oh, see that? Bad connection. This is what spares are for. Turn the circuit off because I don't want to be fooling around with live wire. Okay. Swap this out here. And then this light goes back on again. All right. This one's only going to be consuming 12 volts by itself. Okay. Because it's the only thing in the circuit. So keep that in mind. Series circuit only has one pathway. A series circuit, the total resistance of the circuit will add up to all of its resistance values. The total voltage consumed in the circuit will add up to the source voltage. Okay, there's plenty of these details that you will pick up with me. Okay, and when we do our hands-on lab, we all eventually meet back up again. Okay, so here we go. Now, I want to show you a little bit about, oops, it's a no-no, how to measure things with the meter. Okay? That's not the one that's wrong. We'll save that for later. Put this off to the side. So, first things first. Let's give the shakedown again on strictly the meter this time. So let me make sure you can actually see that and line that up. It looks like you're okay. When you're measuring volts, make sure that the meter is on volts, direct current. That's the straight line with the 3 dashes underneath. Black is in common, red is in volts, okay? Now these tests that you're doing, you have 2 tests you do with a voltmeter. The first test you'd use with the voltmeter is called available voltage. This means how much voltage is available, not how much voltage was consumed, how much is available. It's right there in the name, available voltage. So you ground your meter. Now, ideally, you're going to ground it at the negative post of your battery on the car or a good chassis ground. But since this is a little sketchy right here with the way it's set up, we're going to go ahead and use this one. It will suffice from now. But you ground your lead. You leave this lead right there in the ground. You activate your circuit. Okay? You check your power supply. I have available voltage of 12 volts at my power supply. Okay? I have 12 volts of available power at the very beginning of my circuit. I have 12 volts of available power to my switch. I have Right here, 11.85 volts available after my switch. I have 11.83 volts available to my light. I have 0.09 volts available after my light on the negative side. Okay? Those are available checks. Notice, at no point in time did I say that's how much voltage was consumed or dropped. An available voltage check only checks what's available. One lead on the negative, the positive lead on, the negative lead on negative, the positive lead at whatever test point you're checking. That's strict. Now, if you want to see how much voltage was consumed with any given part, what you do is you need both of your leads, positive and negative. It's the same setup here on the meter. If I want to see how much voltage this wire consumed, I will put my positive lead on the positive side of the component I'm measuring and my negative lead on the negative side of the component I'm measuring. And I see that this wire is consuming 2/100ths of a volt, a little bit more, almost 3/100ths of a volt. Okay, that's good. I want that. Okay, and if I want to measure the switch that's right here, I go ahead and I measure the switch on either end of it, the positive and negative. This switch is consuming about 1/10, almost 2/10ths of a volt. That's a little high for my taste, actually. Oh, there we go, 1/10 of a volt. Sometimes you gotta let the meter settle in. Okay. Also, the quality of your contacts you have here matter as well. Loose contacts create resistance, and resistance consumes voltage. Okay. So now I want to measure this wire. Notice I'm keeping these positive and negative. Positive side of the component, negative side of the component. So I come over here and I measure this wire, and this wire is consuming 4/100ths of a volt. Now, here's the money maker. I want to see if my bulb is functioning and see how much voltage it's consuming. My bulb is consuming 11.7 volts, okay, or 11.74 right there, okay? That's really, really good, and that's what I want to see happening. I look at the ground side of my circuit, okay, and for this case I'm going to go way back over here just to be precise, okay? And my ground side of the circuit is consuming 500, 600ths of a volt. That's good. Now, what the purpose of using a voltage drop is, or an available voltage check, is to see if the voltage applied and a voltage consumed in my circuit is correct. If I see voltage consumption somewhere, if I'm doing a voltage drop somewhere in my circuit, and I see an unexpected voltage, I know I have a fault there, okay? Chiefly, I find an unwanted resistance, okay? And you say, hey, Mr. Linares, I thought we were looking for voltage, not resistance. Well, we have to remember something very, very careful here. Resistance consumes voltage. So if I find an unwanted voltage drop, I also find an unwanted point of resistance, okay? These concepts are going to be beat up over and over and over. So again, this is just study buddy time, a primer. You're going to get plenty of practice with these things, but I'd like you to make a video here so you can see what's going on. Now, let's check resistance, okay? Turn our meter to resistance right here. We turn power off, okay? Now, whatever it is you're going to be measuring, you have to make sure that it is free, okay? That it is free of any power input. Because this meter has a power supply, it has a fuse in it, it has a control switch, it has its own circuit pathway. So whatever it is you're measuring, okay, in case this wire or maybe this bulb or something like that, that becomes the load in its own private series circuit, okay? The meter here is going to send a little micro amount of voltage through it to really precisely check the amount of resistance this has. So what I'm going to do is I'm going to take this wire, I'm going to put my leads in here, okay, being very careful, and I'm going to show that this wire here, we know this conducts, has got 0.1 ohm. That's a good resistance value for a wire, 0.1 ohm, okay? We don't want 1 ohm, we want as low as possible. If we can get lower than that, it'd be even better, okay? But 0.1 ohm seems to be decent right there. Now, let's check our component. So we go ahead and we look at a bulb here. and then we get 0.8, 0.9 of an ohm. Oh, see, sometimes, see, it went higher because I'm moving around. Hold it steady. We have 1.2 ohms. We could drop it. Let's see, keep scrubbing around trying to find the best contact possible. Now I get all the way, no, that's really, really high. See, I thought it was ohms. Right here, you have the M or the K. A capital M is mega ohms, a K is kilo ohms. We just want ohms. Huh. 0.1 ohm. And our leads here don't like this. It's on kilo ohms. So something's really, really weird about my connections, right? Okay, we know that this bulb lights up, we saw it. If it had that many ohms, it wouldn't light up. Wow, we're doing this and we got 152 ohms. We have got a sketchy connection going on here. So let's double check. Find a sweet spot right there. 71 ohms. But we know this lights up, so something's funky going on here, right? In terms of our connection quality between our leads and our sockets right here. See if there's a sweet spot in here. There obviously has to be. I wonder if we do this. Getting better connections with these wires will help. Let's find out. Okay, let's try it like this. Oops. We still show that 70 ohms. Something's funky going on here. Okay, we have an unwanted resistance somewhere in here. So let's find out exactly what's going on here. Let's go ahead and try to light it up and see if we light this bulb up. But the light lights up. If it had that many ohms of resistance, okay, it may not be enough for that voltage to push through. So we're going to double check. We know that that light is actually a good light. Okay, and shame on me for disconnecting it like that without turning it off. Okay, let's see what we have going on here. Okay. Let's go behind this bulb and see what we could see. We're behind the bulb. Let's get in here, see if we can actually get in there. Maybe not. Let's find out. See, once we stab into that bulb, we got 0.3 ohms, okay, 0.4 ohms. So what we have an issue with is the contact between our leads and our terminals right here. It doesn't like it. We're not getting enough good contact. Sometimes that happens and you have to scrub around or find an alternative path to get the truth, okay? So here's our bulb hot here. Nope, the bulb isn't hot. So we could even come over here to the bulb itself and check the ohms value, okay? .8 ohms. That's about right for our bulb, okay? There we go, all right? So we do have a problem with the quality of the connection in here. It's good enough for our wires, but maybe our leads here, maybe they need a little bit of work, or just the material difference between here is affecting things. Let's see what we get on this little tiny bulb here. 4.8 ohms, okay? That's just about what we should have for this kind of bulb, all right? Now, let's unplug these. Let's see if these connections are good. 0.8 ohms, 0.7 ohms, okay? So it's definitely this setup right here that's got something going on with it. Simple way to test things out and see if you have good and bad, all right? And just remember, when you're dealing with ohms, when you're dealing with resistance checks, you're checking the part all by itself, separate from the circuit. Hello, hello, we're just continuing. I had to stop because my meter, as it turns out, has an open circuit in it. I did not check it after the last school year, and it looks like that me lending it out resulted in a fuse opening in it. There's more about that here in a second. So I have a different Fluke meter for us to use. Let me verify that this is in the right spot. Right there, and can we get a little background light and see that? Good. Let's maybe like that. There we go. Okay. So we're going to measure amperage. Now, very much like the other meter, there's a common port here, a volts ohms port here, and an amp port. This one's this one's pretty clear, and it says 10 amps. So when we're going to be measuring amperage here on this meter, we make sure we're on amps up here with our dial. We make sure that we're going to have our negative lead into common right here. Oops, that's a little stubborn. Okay, and then our positive lead is going to go into the amps port here. Okay, again, this is a little stubborn here. We may have to change our leads. Let's see what we get. Okay, hopefully we're connected. Let's find out. Okay, let me do a quick check here. And our leads are not connected. All right. Still not connected. I'm wondering if we have issues with our leads here. Okay, so just to keep things simple, these leads are going to be put to the side. Go back to amps. Okay, and we're going to makeshift our leads here real quick. Now the good news is about tools like your DMM. When you're in lab with our lab boards, these terminals that you use here are the same ones for your leads, so you can use them in your meter. So we're going to have one in common, okay, and we're going to have one in amps, okay. We make sure that we're set up for amps right here. Now what we're going to do is you have your light that's on, okay. You turn your power off. Make sure you break the circuit, because this is the gap right here is where you're going to put your meter, okay? So you take one lead and you touch it to the negative side of your opening. You take the other lead and you touch it to the positive side of your opening. You go ahead and you turn on the circuit, okay? And then you could read the amperage flow. Now see right here, this is measuring AC instead of DC, so boom. DC amps. Right now we are reading 1.9 amps, or just about 2 amps, more or less, okay? Now here's where the big trouble with measuring circuits while they're off or measuring circuits while they're on comes into play, okay? That is heat, like you're getting from your lamp right here, okay? Or from an engine operating, or from hot coolant going by, whatever it might be. Heat will increase the resistance of a material, okay? So when you're checking the amperage right here, you might be saying, wait. When I measured this bulb right here, this bulb had half an ohm, or 1 ohm, I think we measured on this particular bulb, right? So if I have 12 volts, okay, available, okay, and I only have one ohm of resistance right here, okay, I should be having about 12 amps. Well, what happens is when this bulb lights up, the heat goes up, and therefore the resistance goes up, okay? So right here we're looking at close to 2 amps on the bulb right there. That means that if we got about 2 amps while the circuit is on, okay, and then we've got 12 volts that's not changing back there in the power supply, that means that the real resistance of this bulb while it's functioning is around 6 ohms, okay? These things do fluctuate back and forth wildly as a vehicle's operating. So when we're starting off with circuits and we're dealing with them, we have to just understand that for right now, the simple things we're doing with the meter, the simple things that we're doing with these components and these simple parts on here, even though it doesn't look anything like they do on a car, we're just trying to understand the concepts of how to measure, of how the flow works, of what happens when certain things happen with voltage application or resistance increases or decreases and things like that. It takes practice, okay? But for our purposes right now, I was just interested in showing you how to hook up the meter for the various purposes, okay? Which I hope we got you a good start on. You will get plenty of practice on that. I wanted to show you the basic parts of a series circuit, okay, and then get you squared away with what happens when you add resistance to the circuit. And now what I want to do is take you into parallel circuits. So what I'm going to do is stop the video and start another one because this is getting really long, and then we'll go from there. So sit tight, I'll be back shortly with parallel circuits.